All right, guys, welcome. Hey, guys, I want to go over this assignment here, give you some help on this. Now, this should be a review assignment from Honors Chemistry. Obviously, that's older for some of you than others, and I'm not 100% sure how detailed some of the other chemistry teachers got in on this one. So we're going to kind of do A to Z stuff. If you haven't finished this one up, okay, listen in, do and watch and do this again, or finish it up and get it submitted, please. All right, so let's take a look at this. First of all, I want to talk about how things bond. Because you can have resources with you, I would recommend you take your periodic table like this and maybe you add this to us. I don't think it's going to be directly tested like this, but it's a good reminder of how things set up in Lewis dot structures and how they bond. Okay, so what we've been told is you're not going to be asked to draw anything on the AP test, but more than likely not, if you do see this, it'll be a drawing that they show you. Okay, so here's what I have here is I just have the Lewis dot structures for all of the top elements in each one of our families. Okay, because remember, families go up and down, periods go left to right. Okay, so in general, okay, we have the alkali metals, one valence electron, alkaline earth, two valence electrons. They're going to be split left to right. They're going to repel. Boron, aluminum, okay, we'll have the three and a kind of a triangle. Okay, carbon, 1, 2, 3, 4. Nitrogen, oh, missing an electron right here. Okay, two on one side. Okay, and then three singles. Oxygen, 2, 2, 1, 1. Fluorine, 2, 2, 2, 1. And then helium has all eights. Okay, so it does not matter where the open one is. So this one open spot here could be unpaired, could be here, here, here. All right, same with these guys here. The only thing with the oxygen is they have to be adjacent. The two pairs of electrons do have to be adjacent to each other. Okay, how do you pick where to go? Okay, you just basically look at what you're bonding it with and what makes the easiest arrangement. Okay, so I have this. You should also have your electronegativities chart. This was listed, and then these, which are your angle sheets. Okay, so and the one last one, you should also, this is the information, I'll put this on there too, I think I put it on there, which shows you what is the range for electronegativity difference. Okay, so basically the greater the difference, the more we trend towards an ionic type bond. Okay, we're also going to always say that a metal plus a non-metal will fall in this category. All right, that's typically how we define those. Okay, covalent is typically, all three of these are ranges of covalencies. So non-metal plus non-metal. Okay, we can have some nonmetals that do act like as if they are ionic if they reach this level of difference. So I'm going to go through a couple of these. We'll draw them out, and then we'll look at their geometries, and we'll discuss why they are polar or not polar. Okay, so I'm just going to kind of pick from these so you can check some of the ones that you did. CH3F. Okay, so carbon, I'm going to stick right here in the middle, because I know that it bonds 4 times. So it tends to be a central atom. All right, and hydrogen, okay, hydrogen's over here. It has its 1 valence electron. And I also have fluorine, which has its 7. Okay, so hydrogen having only 1 is going to make it a good candidate to be what we call a terminal atom. Okay, so it's going to bring in 1 electron, all right, and it's going to create 1, 2, 3 bonds. Okay, and then we've got fluorine over here, which has its 7. Okay, and it's also going to bond. Now, all of these are non-metals. Okay, which means they are highly attractive, and we need to establish what is the difference in electronegativity. So that electronegativity comes from this chart. This was also in your Chem Bible, and here's our value for hydrogen, which is 2.1. So the H to C bonds are 2.1 and the carbon is 2.5. Okay, so our difference here is a 0.4 difference. It doesn't matter if it's positive or negative, but it is not going to be strong enough to create a dipole, okay? And basically a dipole is where one of these elements is going to be more attractive and it's going to pull this electron that's in the pair closer to it, making it a little bit negative, okay? So the CH, 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 these three bonds here are not polar. Now, as a contrast to carbon to fluorine, okay, carbon, that's our 2.5, and fluorine is 4.0, okay? That equals a difference of 1.5, okay? That is very strong. This is a very strong dipole, okay? And we see that difference listed in our chart, okay? So when we were looking at our range, okay, it's a very polar covalent type bond. And what polar covalent means is that this fluorine, highly attractive, is going to pull this electron that it's bonding with carbon closer to it, making this side slightly negative and the carbon slightly positive. So what is formed is this thing called a dipole, and we represent those with these arrows with the plus at the end. And the plus represents that the carbon is getting a slight positive charge because the electron it's sharing with fluorine is getting pulled towards the fluorine, and the tip of the arrow points towards fluorine. Okay, so this here is going to be a molecule, and if we look at our shapes here, these shapes represent the different molecular configurations that we have. And we do the shape around what we call a central atom. Now, I'll do one here that's a little bit bigger molecule, but we can actually, atoms can have multiple shapes within them. Okay, we're just going to pick what is the center one. Okay, and this is based on things called steric numbers, and steric numbers are either bonds or unpaired electrons. So for example, this here, the X is an element, the other X is an element, and this is an unbonded pair. So I've got 1, 2, 3 connections, okay? One of the connections being an unbonded pair, the other two being bonds. Now, I'm going to highlight a couple of these, and I suggest you do the same. And these are all the ones that are going to show symmetry. Okay, and that's going to be important in a minute because it is going to determine partially whether something, a molecule, will be polar or not. Okay, the first thing we look at to see if something is polar, to see if it has a dipole. Okay, this one does, so this has potential. The next thing we want to do is see if it has any dipoles that cancel out. Well, because this only has one dipole, it doesn't have anything that can cancel out. So this is considered a polar molecule. Now, how polar is this molecule? Well, it partially depends on how many of these dipoles it has. So for example, if I look at this, I've got a dipole hanging off the end, but the rest of this molecule is not polar. Okay, so when I see this dipole here, a positive and a negative, it's only polar on one side. So if I compare it to a molecule like this, which one of these two molecules do you think is going to be more polar, A or B? If you said A, you'd be correct. The reason is because look at this molecule. Look at all of this carbon to hydrogen. This region here, it's not polar. Okay? There's no polarity to that. The only polarity dipole we have is right here. Okay? So is this a polar molecule? Yes. But if I'm given a choice between A and B, B is going to be the one I'm going to, or I'm sorry, A is the one I'm going to choose to be more polar. Okay? And that's because it has one region that is polar, 3 areas that are not, as opposed to this has one area that is polar and 1, 2, 3, 4, 5, 6 bonds that are not. Okay, so this is going to be more polar. Okay, and what that means, polar, think about it like a magnet, is how much of this molecule has a positive charge side or a negatively charged side. And that's going to be important because the more polar something is, the more it's going to stick to it. Okay, so here's an example of CH3F, and then this is a larger one. Let's take a look at, let's do the shape. Didn't do the shape. Okay, so here's the deal. I've got 1, 2, 3, 4 atoms attached to a central one. We call that a steric 4, and it looks just like this one. This is another handy sheet. I don't think they're going to ask you to name things, but it's good to see what they are. And notice that this is a way to draw a three-dimensional molecule on paper. And so, but these are equally repelling each other. This term here, VESPR, valence shell electron pair repulsion, this is kind of showing us that like electrons inside of bonds are going to repel each other and create these kind of neat geometric shapes, okay? And what can repel is not only a bond, but also unbonded electrons, because they're negative too. All right, so I want you to walk you through a couple more of these here. Let's do Cl2. It's a fairly simple one. So chlorine has its 7 electrons. Okay, and I'm going to put 2 of them together. This one here is not going to have a shape of its own. It's going to bond like this. Chlorine's electronegativity is really high. It's a very attractive element, 3.0 and 3.0. But its delta En, the difference in the negativity, is 0. So there is no dipole. This is not polar. Now, here's the thing about things that are diatomic. Okay, so Cl2. That are not polar. Things that are diatomic and are not polar, they tend to be gases. And that should make sense because for an order, we're going to talk about this more in the next video, in order for things to come together and stick together as a molecule, they have to have a certain level of attraction. Well, if it's not polar, there's no imbalance of positive and negative electron, or positive charged nucleuses and negative charged electrons to cause them to come together. Okay. Now, this is a little bit of information about solids that are ionic. Something like an ionic solid of NaCl. Why is that always going to be a solid? Why are ionics always solid? Well, it's because Na is positive and chlorine is negative. And what ends up happening is these end up sticking to each other because they are very positive and very negative. So we end up having this repeating arrangement that is going to cause them to be highly attracted to each other. And so in an ionic compound, we see the Na attracted to all the chlorines that are going to surround it, and the chlorines attracted to the metals. Now, this is a molecule or a compound, this is a compound, and they're going to stick like this together. Now, this also explains why table salt, which that's what this is, has a cubed arrangement, is because these molecules nicely stack with each other. So high attraction is because is going to form things that are solids. So the general rule with polarity and how they interact with other molecules is if it's polar, it's going to stick to other polar things. And if it is nonpolar, those things don't stick to each other quite as well, just like we see here with the chlorine gas. Okay, so there's now this one has no shape, okay, because we need at least 3 atoms to have a geometric shape. Let's try a couple more of these. Oh, let's do the CO2. I'm going to put carbon in the middle. Okay, 1, 2, 3, 4. I'm going to put 1 oxygen over here. Okay, and the other one over here. Okay, now each one of these oxygens will bond twice, just like this. Okay, so that's kind of the messy way to draw it. We can actually make this look a little bit neater if we draw it like this. Okay, so each one of these bonds is represented by a line, and then we have the unbonded electrons on the outside here. Now notice that I moved them to the side. That's because we have 1 region, 2 regions, 3 regions of negative, which means these electrons are going to repel these electrons, which are going to repel these electrons. Okay, if I look at This, it's kind of like a triangle shape, okay? We're going to do the shape based off of the center atom. Now, the center atom here is carbon. Carbon is bonded once to this and once to this. Now, twice to oxygen on the right and twice to oxygen on the left. Now, just because it's bonded twice does not mean it gets counted twice for the steric, okay? Steric is the number of connections that are made. So we're connected once to the oxygen on the right and once to the oxygen on the left, okay? That's going to give us a linear type shape. So our shape is linear. And as long as these two elements are the same, this is going to give us a nonpolar atom. Now, let's look at the electronegativity really quick. So this is 2.5 for carbon, and oxygen is 3.5. So this is going to create a dipole. In fact, it's going to create a dipole going in opposite directions. But check this out. Because they are going in opposite directions, and this is a symmetrical atom, these are going to cancel each other out, okay? So this has polar bonds, but it is a non-polar molecule, okay? And we have evidence that this is non-polar too, because CO2, guess what state of matter it is? It's a gas, okay? Because even though I have these two dipoles here, they cancel each other out, which means this molecule is largely unattracted to other molecules around it. When molecules aren't attracted to other molecules, they're in the gas form, okay? So one thing we can tell about the attraction between molecules is their state of matter, okay? So solids have higher attraction between their molecules, and gases have very weak attraction between molecules. Liquids, they're kind of in the middle. Okay, all right, so that is CO2. We did a linear shape there. I'm going to jump down to this one right here. Let's do a little bit, let's see, maybe I can, yeah, let's do a little bit bigger one, okay? Let's see, so we've got carbon, 1, 2, 3, 4, and I've got 3 hydrogens with that, 1, 2, 3, let's see here, what else we have? Nitrogen. Okay, so I've got nitrogen. Nitrogen has 1, 2, 3, 4, 5. Okay, and I've got 2 more hydrogens. So 1, 2. Okay, so here we go. Here's what we have. So I know, let's see, electronegativities, let's put those on here. Nitrogen is 3.0, carbon is 2.5, hydrogen is 2.1, and 2.1. Okay, so I've got lots of bonds going on here. So I've got carbon to hydrogen. My delta En for this is 2.5 minus 2.1 is 0.4. I do have a carbon to nitrogen. And that delta En is equal to 0.5, and then I have my nitrogen to hydrogen. And let's see, that's 3.0 and 2.1, so the difference there is 0.9, okay? So when I look at my polarity here, okay, so I've got a polar bond, okay, so this is polar. This is even more polar. Okay, and this is not polar. Okay, so I've got some things here to work with as far as this molecule. So my N to H, these are really big dipoles, and I put the arrow towards the end because it has a higher electronegativity, means it's more attractive. It's going to pull the electrons towards it. Between the carbon and the nitrogen, let's see here, the nitrogen is still more polar. Okay, so we're going to do this. All right, so in general, okay, I'm going to look at this one. I've got one bond, one connection here, one connection here, one connection here, and then an unbonded pair. So that means I'm going to have a steric number of 4. So unbonded pairs like this around the central atom is going to be 1, 2, 3, 4. Now you're like, wait a minute, why did you pick this one and not this one? Well, this molecule actually has 2 different shapes. One where this is the central atom and one where the carbon is the central atom. All right, so let's take a look and see if this is going to be what its shape is for around the nitrogen. Okay, so I'm looking at steric 4, and if I go over here, I've got one lone pair, so it's going to match up with this trigonal pyramid shape. So this is a trig pyramid shape, and it is not going to be polar, okay, because they don't cancel out. Only the ones that show perfect symmetry are going to cancel out and be nonpolar. So this here will be polar, okay? And my shape here is trig pyramidal. Okay, now I'm going to go over here. I've got 1 connection, 2 connection, 3 connection, 4 connection. Okay, and this shape here is tetrahedral. Okay, so you're not probably going to see that on a whole lot of these, but I just wanted to show you what that looks like. Okay, so hopefully that gave you a little bit more of insight of what that is. The next lecture is going to be about just molecules and how they interact with each other. Okay, so we're going to talk about hydrogen bonding, London dispersion forces, ionic compounds, and how they interact. All right. So hopefully that was helpful. If you have any questions on these, please let me know. Hope you are well.